Okay, let's consider this problem involving specific heat capacity and calorimetry. Consider 42.3 grams of iron at a temperature of 97.2 degrees Celsius. If the iron is added to 112 milliliters of water at 22.1 degrees Celsius, determine the final temperature of the water-metal mixture. Okay, so first we can set up an equation Q equals mc delta T for the iron and for the metal. The iron is hot, it's going to lose some amount Q. So for the iron, let's set up this calculation. Now it's going to be a negative value because it's losing energy, it is cooling down. So the mass of the iron is 42.3 grams. We would look up the specific heat capacity for iron on a table and find that it is 0.45 joules per gram degrees Celsius. And we need delta T. Now we don't know the final temperature of the iron. That's part of the problem we're trying to solve. So we'll just call it TF, but we do know its initial temperature, 97.2 degrees Celsius. All right, there's our negative Q equation for the metal. The iron is going to lose that much energy. Now, whatever this number is, that's how much energy the water is going to gain. So let's set up an equation for the water, knowing that the value for Q, the number, is going to be the same number as the number for the iron, and it's going to be mc delta T for the water. So again, we have 112 milliliters, which is 112 grams, because the density of water is 1 gram per milliliter. Okay, we know the specific heat capacity for water, and if we don't, we can look it up. And again, we don't know delta T, that's what we're trying to, or I'm sorry, we don't know delta T and we don't know TF, that's what we're trying to solve for. The TF for the water is going to be the same TF for the metal because they're mixed together. They will eventually reach the same temperature. And we know from the problem that it starts out at 22.1 degrees Celsius, so let's put in our 22.1 degrees Celsius. Okay, so we have two separate equations, and we can set them equal to each other, remembering that the iron has to lose energy. So what I'm going to do is I'm going to rewrite all of these pieces. The iron is going to be negative 42.3 grams times all of this. Okay, and that is going to equal mc delta T for the water. All right, and now we have one long equation with one variable that we can solve for algebraically. Okay, solving algebraically, we get the following. So I'm first going to multiply these two values. So I'm going to get negative 11.9, and then I will have to distribute that across the temperature change equation there, remembering to pay attention to the signs. And that's going to be equal to the right side of the equation, the mass times the specific heat capacity, which is 469, and that's going to be multiplied times the temperature change formula for the water here. Now, if I distribute, this is simple algebra that we just need to practice and pay attention to our signs. Remember, negative times a negative will make this a positive. Okay, oops, and that's 57, oops, 1157. That is a 7, sorry, equals 469 temperature final minus 10,365. All right, now we need to get the like terms together. TF, so I've just added 11.9 to both sides of the equation for the TF, and now I'm going to add 10,365 to both sides to cancel here. And that will give me 12,522. Now divide both sides by 480.9. And I solve for TF, which equals 24 degrees Celsius. The mixture should be 24 degrees Celsius. Two things you want to check. Sig figs. We are limited because for the iron, we only had two significant figures. for the specific heat capacity. The other thing we want to look at is this temperature somewhere between our two initial temperatures? 24 degrees? Well, it's between the 22 degrees of the water and the 97 degrees of the metal. So it's likely correct. And there you have it.